Hello everyone, welcome back to another lesson in our Digital Systems video series. In this lesson, we're going to begin our study of truth tables. We'll learn what a truth table is, why it's so important in digital systems, and how to correctly construct one from a logic function. We'll also learn how to determine the number of inputs, the number of rows, and the overall structure of a truth table. So let's get started. So far, we've been working with one way of representing logic function, Boolean expression. But it is not the only way to represent a logic function. As you can see here, there are several different forms of representation. And notice that Boolean expression and truth tables are part of Boolean Algebra, which means our study of Boolean Algebra continues as we move into truth tables. So even though we are changing the form of representation, we are still working within the same mathematical framework. And now we're going to focus on another very important one, the truth tables. The logic doesn't change, only the way we represent it. In many textbooks, truth tables appear later, but here we're introducing them earlier to help you better understand how logic functions behave. Now, let's define what a truth table actually is. A truth table is a way to represent a logic function by listing all possible combinations of input values and showing the corresponding output for each case. Each row represents a specific input condition. In other words, for every possible input combination, the table tells us what the output will be. So a truth table doesn't just represent a function, it shows how that function behaves. Just a quick observation. You often hear me using terms such as input values, input combinations, number of rows, and input conditions in the context of the truth tables. These terms are closely related and often refer to the same idea, okay? At this point, we are going to move a little more slowly. In this first lesson, I want you to focus on just one thing, how to build the structure of a truth table. In other words, we are not going to worry about filling in values yet. Right now, the goal is to understand how the table is constructed. So the question is, given a logic function, whether it's represented by a Boolean expression or digital circuits, how do we determine the size of a truth table? First of all, we need to identify how many inputs the logic function has, because the number of rows in the truth table is given by a very simple expression, 2 to the power of n. Now, let's understand what this means. The base is 2 because in digital systems, we use binary values 0 and 1 to represent bit states or logic states. And this exponent n represents the number of inputs variable in the circuit or in the Boolean expression. So once we understand this, we can determine how many rows a truth table have, based on the number of inputs in the circuit or in the Boolean expression. Here I've included this small reference table to help you visualize this, okay? For example, even with 0 inputs, we will still have one possible condition. If we have a circuit with 3 inputs, then we use 2 to the power of 3, which gives us 8. So the truth table will have 8 rows, that is 8 input combinations or input conditions. And if we have a logic function with 4 inputs, then you use 2 to the power of 4, which gives us 16. So the truth table will have 16 rows, that is 16 input combinations. So the number of inputs directly determines the size of the truth table. Now let's take a closer look at the structure of a truth table. I've included this example here so you can understand each part of it. At the top, these columns represent the inputs of the circuits. So here we have input A, input B, and input C. Each one corresponds to an input variable. Typically, the leftmost variable changes logical value more slowly. That's why it's called most significant bit, or MSB, okay? While the rightmost one changes more frequently, and it's called least significant bit, or LSB, okay? Don't worry, it will be clear in the next lesson. Now the last column represents the output. This column is essential because it shows the results of the logic function. For each combination of inputs, we will determine the corresponding output. So each row contains a combination of logical values, zeros and ones, and these combinations directly affect the output of the circuit. You may notice this index column on the side. It simply labels each row. Row 0, row 1, row 2, row 3, and so on. For now, you can ignore this column if you want to, but it becomes very useful later on, especially when working with canonical forms, kernel maps, or other digital systems. Alright, let's take a closer look at this example. Here we have a Boolean expression and we want to build its truth table. You might be thinking, but isn't this just one input? Yes, it is. But even with a single variable, this is still a Boolean expression, and it still represents a logic function. So now, using our reference table, how many rows will this truth table have? Just remember the rule. The number of rows is given by the expression 2 to the power of n, where n is the number of inputs. In this case, we have only one variable, so n equals 1. So we calculate 2 to the power of 1, which gives us 2. That means this truth table will have 2 rows. In other words, 2 possible input combinations. It's very simple. Now let's move on to another example. Here we have a Boolean expression with 2 variables. So in this case, we have 2 inputs. That means n equals 2. So we calculate 2 to the power of 2, which gives us 4. That means this truth table will have 4 rows. In other words, 4 inputs combinations, okay? As we increase the number of inputs, the number of combinations also increases. Let's move on to the third example. Here we have 3 variables, A, B, and C. That means we have 3 inputs. Using the same rule, 2 to the power of n, since we have 3 inputs, so n equals 3. Therefore, we calculate 2 to the power of 3, which gives us 8, which means the truth table will have 8 rows, 8 input combinations. It's very easy, it's very simple. Let's look at more example. Here we have a Boolean expression with 4 variables, that is 4 inputs. A plus B plus C, all these being multiplied by D. Then we have 4 inputs. So in this case, n equals 4. Therefore, we use 2 to the power of 4, which gives us 16. So the truth table will have 16 rows, 16 input combinations. Now let's look at a very important detail. Many students see an expression like this, okay, and assume that it represents 4 inputs. But that is not correct. Pay close attention. To determine the number of inputs, we do not count how many times variables appear. We only count the distinct variables. In this expression, we have A, B, and C. Even though A appears twice, it still represents only 1 input. So this is a circuit with 3 inputs, not 4, okay? Therefore, n equals 3. So we calculate 2 to the power of 3, which gives us 8. So the truth table will have 8 rows, okay? Remember, repeated variables do not create new inputs. Now, let's look at the same idea, but this time using a logic circuit, okay? At first glance, some students may think this circuit has 4 inputs because the signal A appears in 2 different places, okay? Here and here. But that is not correct. This is still the same input A being used in more than one branch of the circuit, okay? To count the inputs of the circuit, we count only the distinct external inputs. In this example, the inputs are A, B, and C. So this circuit has 3 inputs, not 4. Therefore, n equals 3. So we calculate 2 to the power of 3, which gives us 8. The truth table will have 8 rows, okay? All right, let's practice with our first exercise. Take a look at this Boolean expression. I'd like you to pause for a moment and try to answer this question. How many inputs does this function have? And how many rows will each truth table contain? Pause the video and try to solve it by yourself. Okay, if you already tried it, let's solve it together. First, we need to identify the distinct variables. In this case, we have A and B. Pay attention. Even though A appears more than once, it still represents 1 input, okay? So this function has 2 inputs. Therefore, we use 2 to the power of 2, which gives us 4. So the truth table will have 4 rows, okay? Great job if you got that right, okay? Let's move to the next exercise. Take a look at this Boolean expression, okay? Once again, I'd like you to answer, how many inputs does this function have and how many rows will each truth table contain? Alright, let's check it together. First, let's identify the distinct variables in the expression. Here we have A, B, C, and D. So this function has 4 inputs, which means 2 to the power of 4, which gives us 16. That means the truth tables for this function must contain 16 rows, alright? Notice that the complexity increases quickly as we add more inputs, okay? Now let's finish with the final challenge. This time we have a more complete example. We can see the Boolean expression and we also see its logic circuit representation, okay? So here's the question. How many inputs does this function have and how many rows will each truth table contain? Pause the video and try to solve it by yourself. Okay, if you're ready to try it, let's solve it together. Okay, as we did before, we identify the distinct inputs. And here we have the input A, input B, and input C. Even though some variables appears more than once in the expression and in the circuit, they still represent the same original input, okay? So this function has 3 inputs. Therefore, n equals 3. So we calculate 2 to the power of 3, which gives us 8. That means the truth table for this function must contain 8 rows, okay? Excellent work! In this lesson, we learned to determine the structure of a truth table by identifying the inputs and calculating the correct number of rows. In the next lesson, we'll learn how to correctly fill the input combinations. Thanks for watching, and I'll see you in the next lesson.